Swayam Prabha. Digital India. Educated India.
Welcome to this session on ultrasonic machining under the course Advanced Manufacturing Processes. We have already covered two other processes like abrasive jet machining process and water jet machining process and water abrasive water jet machining processes under the category of mechanical processes in the advanced manufacturing processes. Today in the same series, again in the mechanical energy based processes, we will try to discuss one more process named ultrasonic machining process. This process is very popular, also known as USM, and this is particularly useful and popular in the ceramics and glass industries. Let us move on to some details of this process. This process is a mechanical material removal based process, as I said already. This process is used to erode material in the form of fine holes and cavities in the hard or brittle workpieces. The process uses form tools, vibrations of high frequency, usually in the range of ultrasonics, something around 20 kilohertz and above, and as a suitable abrasive slurry which contains one medium and one abrasive material like boron carbide, silicon carbide, etc. The ultrasonic machining, also called USM, is suitable for machining glass, ceramics and semiconductors for increasingly complex operations to provide intricate shapes and workpiece profiles. This USM is a non-thermal and non-chemical process which creates no change in the chemical, physical or metallurgical properties of the workpiece. It is therefore widely used in the manufacturing of hard and brittle materials which are commonly infeasible to machine by other non-traditional methods. The cutting is actually performed by the abrasive particles which are suspended in the slurry. The ultrasonic machining accomplishes the material removal through abrading action of the grit loaded slurry which is kept circulated between the tool and the workpiece. This is schematically. A tool is something like this and this is the target workpiece or work surface to be machined. A slurry is made to flow through this. So, this is slurry of which contains a medium plus abrasives. We will talk in details about this medium and this slurries later on. These abrasives can be boron carbide, say B4C, or can be silicon carbide and so on. Now, this tool will be vibrating at the ultrasonic frequency and this will be in excess of or something like 20 kilohertz or something like this, and this slurry will be made to flow through this in this zone. Therefore, the abrasives will come in contact or in this zone something like this, then this tool will hit these abrasive particles, which will in turn hit this work surface and causes brittle fracture on this workpiece surface. Then as the process repeats, then this workpiece surface gets fractured and the material from this will slowly get dislodged, and since the slurry is flowing continuously, these dislodged particles will be taken away by this. So, these are what we call dislodged particles from the workpiece. So, this is the work part to be machined. So, therefore, as this is the shape of this workpiece. So, this will hit these particles on this corresponding area on this workpiece. Therefore, this workpiece will have an impression of the replica of this tool or the heating feature we are using in this case. So, this will replicate this is the machined part or machined feature you can say on this workpiece. This is the workpiece and this is here the tool and this is here the tool. So, this is the basic principle of ultrasonic machining process. In this process, small amplitude and high frequency of vibrations are given to the tool, typically in the range of 10 to 20 micrometer at 20 to 40 kilohertz, as I have already told. The hard abrasive particles in the slurry are accelerated towards the workpiece surface by oscillating action of this tool through the repeated impacts. The tool further machines a cavity of the cross section identical to its own, as I have already explained. A replica of the tool will be produced on the workpiece surface. The material removal takes place in the form of fine grains by shear deformation. Different mechanisms could be attributed to this material removal process. There are mainly 4 mechanisms, known mechanisms I should say. There may be some others, but not much evidences are being produced. However, some evidences are available as far as these 4 mechanisms are concerned. Number 1 in this is the hammering action that causes brittle fracturing of the work material. Then number 2 is the impact action of the abrasives that causes stress concentration on the workpiece surface and eventually the crack formations and dislodgement of the material. Then cavitation effect, which is the consequence of very rapid acceleration of the abrasive particles in the medium that causes a pressure difference, which ultimately creates a shock wave, and that ultimately causes, as the shock waves proceeds and the bubbles collapses, then material removal takes place on the workpiece. Then the 4th action or mechanism of material removal is the chemical reaction due to the slurry. As we have said, there is a medium. So, this medium may contain some chemical agents which may cause some chemical reactions on the surface of the work material. Generally, as we remove some material from the work surface, the newly developed surfaces will be nascent surfaces and they will be very prone to the chemical attacks. Therefore, it is possible that at this stage itself the chemicals, if present in that slurry or in that medium, might cause some reaction with that nascent surface and which may eventually cause material removal in the form of corrosion or in the form of reaction materials from the workpiece surface. So, these are the 4 basic mechanisms, known mechanisms as far as the ultrasonic machining is concerned. The workpiece shape and dimensional accuracy is directly dependent on the geometry of the tool. The schematic of ultrasonic material removal process is shown in the figure. So, here this is the basic figure of this ultrasonic machining process. So, here is the slurry is being fed or kept on circulated. This slurry contains one medium which is very popularly water H2O, and on this some other abrasives like B4C boron carbide are being added, and this concentration of this will vary depending on the application. Generally 30% or 40% of this abrasives will be added to this material, and the sizes of these abrasives will also vary. It can be 1 micron and it can be up to 25 micron or 40 micron as well, and accordingly the material removal or the cutting rate will also vary depending on the size of this abrasive materials. So, basically at this stage let us consider a mixture of this water plus abrasives are coming to this cutting zone where the machining is to be needs to be carried out, and this is the tool, this is the tool, and this is the tool holding or the horn assembly which will impart ultrasonic movement to this tool, and this will be vibrating as shown here at some frequency, predetermined frequency, something around 20 kilohertz or more, and this will cause these abrasive particles to accelerate towards this workpiece at a very high velocity, and they will impact on this work surface with this energy. Energized particles will hit this work surface with very high energy, that is kinetic energy, and therefore, this surface will get fractured by brittle fracture mechanism because of this. Moreover, this hammering action of this tool will take place on this surface because of this movement of this tool. So, hammering and impact, as well as since this particles will be accelerated at a very high speed, as I said earlier, cavitation will also take place because of this pressure difference due to the acceleration of these particles in this media. Moreover, the chemical action may take place, and these are the 4 mechanisms that will take place in this. Also added to this, while these particles will come out through this will abrade this side of these workpieces to some extent, and that may also cause the material removal on these sides, and therefore, some sort of machining will take place on the sides of this workpiece as well, in addition to the basic material removal on this direct work surface. This is known as side cutting. So, this is the setup as a whole, the ultrasonic setup. So, this is the loading system, and this is the cone, also known as concentrator or the horn assembly, which concentrates the ultrasonic vibrations that is being generated here inside this. Some generating mechanisms are there, devices are there, and this ultrasonic frequency is being concentrated to the tool or given to the tool head. This can take any shape as per the requirement. It can be square, it can be cylindrical, or and so on, so forth, and the slurry will be kept on flown through this slurry system, where there will be pump and filter systems, etc. Pump for keeping this slurry flown, and filtering for filtering some of the particles, unwanted particles from this system. Of course, there will be some stirrer kind of arrangements for keeping that slurry concentration uniform, and workpiece will be suitably clamped here and the machining will take place in this zone. This frequency of this oscillation and this load on this can be varied as per the applications, and also I must mention here that this configuration, this is a vertical configuration as far as this ultrasonic setup is concerned. However, a horizontal configuration is also possible in this ultrasonic machining case, in which the tool will vibrate in this direction rather than this. Let us have a quick look at the historical developments of ultrasonic machining process. The development of this process USM started way back in 1927. However, this was accidentally discovered during investigating the ultrasonic grinding of abrasive powders. It was found that the surface of a container which was holding the suspended abrasives disintegrated as soon as the tip of an ultrasonically vibrating transducer was placed close to it. The further interesting thing was the shape of the cavity thus produced accurately reproduced the tip of the transducer. This was the first indication that through ultrasonic machining a tool shape can be reproduced on the job. In the early 1950s, industry started realizing its benefits and the production of ultrasonic machines began following that. A wide range of brittle materials including glass, ceramics and diamond can be effectively machined through this process. Let us see the process, how it goes. The ultrasonic processing is performed using a desirable tool along with the abrasive slurry as a media. The cutting tool oscillates at high frequencies, typically in the range of 20 to 40 kilohertz. The shape of the tool corresponds to the shape requirements in the workpiece, as I have already mentioned. It can take any shape. The abrasive grains are driven by the high speed reciprocations across the small gap in between the tool and the workpiece, as already discussed. Uniform force is used to gradually feed the tool. The impact of abrasives is the energy source that is mainly responsible in material removal. Due to the impact of abrasives, the material removal takes place in the form of small wear particles which are carried away by the abrasive slurry. Due to the abrasive action of the particles, gradually wear of the tool occurs, thereby requiring the tool to be made of tough materials. Tough materials means, as we know, it will be able to absorb shock to some extent. Because this works in the impact principle, therefore, the tool as well receives some impact of the abrasive materials and it should be capable of absorbing this impact as well. And higher the shock absorption capacity, better will be the tool life. However, at the same time it should be able to deliver energy to the working particles as well. Let us have a look at the mechanisms of material removal in this process. Although the USM process is commercially used since many decades, the exact details of mechanism leading to the removal of fine materials is yet to be understood well. The main mechanisms responsible for the material removal in ultrasonic machining are as follows. Number 1 is mechanical abrasion. This occurs due to the hammering effect of the abrasive particles on the workpiece through the tool. Number 2 is the impact. The freely moving particles impact with a certain velocity on the workpiece, which results in micro chipping on the workpiece surface. Number 3 is the erosion mechanism. This is due to the cavitation effect on the abrasive slurry, which causes erosion of the workpiece surface. And number 4, as I have indicated earlier, is the chemical action. Due to this, the fluid in which some chemical agents may be present, the chemical effect can come into consideration. It has also been reported in the literature that among the above mentioned mechanism, the first two, that is hammering and mechanical abrasions and impact, are primarily responsible for major stock removal. Investigations reveals that erosion plays a lesser role in the removal of material from normal materials. However, for the porous materials, it is observed that erosion due to cavitation is a significant factor. Next, let us see the schematic presentation of an impact and possible mathematical interpretations of the impact due to a single grain. So, this is where the abrasive is and it is being hammered on this workpiece. Suppose this is being inserted or it is indenting the workpiece by a distance something like h. The diameter of this particle is say d, and the diameter here at the impact point, the maximum diameter is capital D. Then the geometry can be represented something like this. So, this is the d by 2 distance and this is small d by 2 minus the height of the indentation. This is the height of the indentation. Now, using this trigonometrical relations of this geometry, then we can arrive at something like this. D by 2 square is equal to small d by 2 square minus d by 2 minus h whole square, which eventually gives d is, that is the diameter at which the abrasive is impacting or indenting is approximately equal to 2 under root d into h. Since h is very small in comparison to the diameter of the particle, therefore, this can be arrived at. And finally, it can be shown that material removal rate q is proportional to the velocity, the volume per impact, and then the frequency of this striking tool or the striking abrasives. Now, let us look at the advantages, major advantages of this process, ultrasonic machining process. First of all, there are no physical or chemical or thermal changes on the workpiece, and there is no physical contact. The microstructures reveal that there are also no structural changes as the stresses induced are too less. The cutting forces being low, workpiece is unstressed, undistorted and free from thermal defects. There is no direct contact of the tool and the workpiece, due to the slurry used, and it makes it a wet cutting process. The surfaces so produced are free from stress and damages. This is very significant as far as the process is concerned or the produced part is concerned. The process is free from bars and distortions as well. Therefore, the process is suitable for any materials irrespective of electrical conductivity. However, the process is very much suitable for machining brittle materials essentially. The process offers good surface finish and structural integrity as well. Let us look at the disadvantages or limitations of this process as well. Soft materials like lead and plastic are not suitable for machining by this process, since they tend to absorb the abrasive particles rather than to chip under the impact. As I said already, this is a process where the impact energy is used, and therefore, if the material itself absorbs the impact energy, then there will not be any crack development, and therefore, the failure of the material or the final material removal will not take place. And therefore, these materials that absorbs energy like soft materials are not good candidates for machining using this ultrasonic machining process. The ultrasonic machining process consumes higher power and has lower material removal rates as compared to traditional fabrication processes. In this process, high frequency electrical energy is converted into mechanical vibrations through a transducer. The high frequency vibrations are transmitted to the abrasive particles in the slurry via an energy focusing device, also called horn or tool assembly, as I have already indicated during the beginning of this session. Further point is the tool wear rate in USM process is fast. Like this can be explained like this. In this process, as I told, the tool will hit the abrasive particles something like this, and this abrasive particle will in turn hit this work surface. Now, as this tool comes in contact with this abrasive particle, so therefore, there will be an impact on this, on the part of this tool as well. So, this is the tool and this is the abrasive. Therefore, what happens, this tool also undergoes some sort of stresses under the impact of this, and we should remember this is moving at very high frequency, which is something around 20 kilohertz or more. Therefore, this tool end is also susceptible for wear during the process, and in fact, it gets worn out very frequently while working with this process. Therefore, this tool needs to be changed very frequently. In order to overcome this process, generally this tool material is generally little tough materials are selected. Generally stainless steel are good work materials in this case, and it has got considerably better work life. Otherwise, some other materials are also chosen. As the USM process continues, the lateral wear of the tool increases gradually, and it tends to make the holes tapered. This is also another problem as far as this USM is concerned. the sharp corners of the tool get rounded off, thereby requiring tool replacement essential for producing accurate blind holes. The accuracy of the machined surface gets lost due to setting up of strong lateral vibrations. So, this can be again explained like this. Because of the continuous impact of this tool, so this is tool and this is say abrasive and this is workpiece surface. So, after some time what happens, this sharp corners of this tool gets rounded off something like this and the resulting tool becomes something like this. So, the sharp features of the tool disappears here, and also this is again reflected on the workpiece as well. Since this replica is produced, therefore, the corresponding hole to be produced will be something like this. So, therefore, a rounded corner or a radius, a rounded corners will appear instead of sharp corners, which ideally should have been something like this. So, this is a kind of inaccuracy associated with this process. This occurs if the axis of the tool and the horn, which are braced together, are not properly aligned with the transducer axis. This might cause the lateral movement of the tool end also. So, that might also give rise to the inaccuracy of the feature or the hole to be produced or cut to be produced. In such a case, the tool needs to be redesigned. The holes produced in ultrasonic machining have a tendency to break out at the bottom, while the static load and high amplitude is used. While producing deeper holes through this method, there is ineffective slurry circulation leading to presence of a fewer active grains under the tool face. Due to this, the bottom surface of the blind holes tend to become slightly concave. As I have already shown, there will be radius formation at the bottom of the hole. That means we can conclude that there the ineffective cutting at the bottom of the hole in case of the hole depth is more. Let us quickly look at the working principles of this process. A recirculating pump forces abrasives suspended in a liquid medium between the vibrating tool face and the workpiece. Then the tool shaped like the cavity to be produced oscillates at an amplitude about 0.013 to 0.062 millimeter at 19 to 40 kilohertz. The tool vibrates the abrasive grains against the surface of the workpiece, thus removing the material. The abrasive particles strike the workpiece at 150,000 times their own weight. These tiny abrasive particles chip off microscopic flakes and grind a counterpart of the tool surface. Let us look at the ultrasonic machine setup. The basic ultrasonic equipment consists of a generator for high frequency oscillations, then an acoustic head consisting of transducer and horn also known as shank or trunk. Then tool and abrasive slurry elements. This is shown in the schematic like this. So, this is the overall structure of the setup, and this is the work table on which the workpiece is being clamped, and this is the working head, also known as the tool. This is where the ultrasonic generating facilities will be located, and the ultrasonic frequencies will be transmitted through the horn assembly or the clamping device to this tool. So, ultimately we will be observing the mechanical oscillations or displacement of this tool head at this point. This height of this tool head with respect to the work table is adjustable through some mechanisms here, and this will be adjusted as per the requirement of the workpiece. And another important component is the slurry circulation system, in which the abrasive and the medium, that is water, will be made and will be kept on circulated and kept on stirred and flown to this zone through some hose arrangement or tubing arrangement. The flow rate can be controlled at this stage. Flow rate of the slurry flowing through this can be controlled very well. So, these are the main subsystems affecting this ultrasonic machining system. The transducer, which is responsible for producing the ultrasonic frequency, the tool holder, which is responsible for giving a rigid clamping of the tool and transmitting the frequency from the transducer to the tool head. Then the tool itself, which will be responsible for producing the accurate feature on the workpiece. The tool will be as per the requirement of the job, and then the abrasives, which will be basically responsible for making contact with the workpiece, which will hit the workpiece and remove the material from the workpiece, and the power supply system to the entire system for producing ultrasonic frequency, for keeping the slurry system flowing, and so on. These are the main basic subsystems in an ultrasonic machining system. As I said, the power supply of the machine comprises of the high frequency oscillating generator, and this generator is responsible for transmitting electrical power to the transducer, which creates energy impulses in the ultrasonic range, that is sometimes starting from 18 kilohertz onwards. The energy pulses are then converted into mechanical vibrations. The primary function of the transducer is to convert these electrical impulses into vertical and two-dimensional strokes. Sometimes it can be horizontal as well, depending on the configuration of the machine. The acoustic head is considered as the heart of the whole equipment, and this mainly consists of two parts: the transducer, which converts the high frequency output of the generator into linear vibrations, and the number 2, the horn or the trunk, which mechanically amplifies the linear vibrations. The transducer, ultrasonic transducer, so here this is responsible for producing the ultrasonic vibrations and is driven by the signal generator, which gets further powered by an amplifier. The ultrasonic machining transducer works on the following principles: piezoelectric effect, magnetostrictic effect, and electrostrictive effect. The function of an ultrasonic transducer is to convert the high frequency electrical impulses from the oscillator into mechanical vibrations. The periodicity of these vibrations periodically shortens and lengthens. For low power applications, piezoelectric transducers are used, whereas for high power applications, magnetostrictive transducers are preferred. Next, let us see the trunk assembly. It is also a critical link in the ultrasonic machining system. This is known by several names such as shank, horn, concentrator and amplifier as well. The trunk amplifies and focuses vibrations of the transducer to the required intensity necessary enough for driving the tool. The increase in amplitude of vibrations at the tool end is obtained by reducing the cross section of the trunk. And now let us see the tool. The tool is designed to provide the maximum amplitude of vibration at the free end. The selection of the tool material is very critical, as I have already indicated. The tool tip is subjected to vibration and it must not fail due to severe wear it has to undergo during the machining process. The commonly used tool materials are brass, high speed steel, mild steel, silver, stainless steel, tungsten carbide and monel metal. The tool is attached to the trunk or the horn by silver brazing process or by hard soldering. At times it is fastened or screwed to the trunk also. The tool material properties and tool geometry. The shape of the tool, solid or hollow, mechanical properties of the material used in tool making are some of the other parameters that may affect the ultrasonic process performance significantly. As we have indicated already, the tool material should be tough in nature. Now, quickly let us have a look at the applications of this process, ultrasonic machining process. This is used in machining hard and brittle metallic alloys, semiconductors, glass, ceramics, carbides, etc. Basically, as we have already indicated, this is a process directed for glass and other hard and brittle materials. The machining of advanced ceramics for applications in auto engine components, this is used. The process is also used in machining wire drawing, punching or blanking of small dies. The process is also used in machining ceramic substrates for drilling holes in borosilicate glass for sensors used in electronic industries. Drilling small holes in helicopter power transmission shafts and gears, this process is used. Now, let us have a very brief summary of what we have discussed today. The ultrasonic machining process is basically a non-thermal and non-chemical process used for machining hard and brittle materials. It can be used for drilling, channeling, profiling and micro machining features which are otherwise difficult to generate with traditional machining processes on hard and brittle materials. The basic components to the cutting actions are believed to be the direct hammering of the abrasives into the work by the tool, which is a major factor responsible for material removal. Next is the impact of the abrasives on the work, and the other two minor mechanisms or the factors are cavitations, cavitation induced erosion and then chemical erosion caused by the slurry. So, with this we have discussed the development of this USM process in this session, then the basic process of this ultrasonic machining, its working principles and then applications, the advantages and limitations of this process. We hope this session was interesting and fruitful. Thank you.